So I'll wait for 2 minutes. Then I will start solving the questions. So I'll start now. There are no joinees. So I'll just start solving the question. First, let me share my screen. So good afternoon. My name is Asma Parveen. I am one of the TA for this course, Environmental Chemistry, instructed by Professor Bhanu Prakash Belanki from Department of Civil Engineering, IIT Roorkee. I am a PhD scholar in Civil Engineering Department at IIT Kanpur. So we will first see a brief recap of what was taught in week 4, and then we will go directly to the previous year questions based on the week 4 material. So let's see. So there are 5 lectures. The first lecture was on ionization fraction for monoprotic, protic, diprotic and triprotic acid. If there is a strong acid, then it will completely deprotonate into cation, that is H plus and the anion. But if there is some weak acid, then it will partially dissociate. Some fraction will be the deprotonated form and some will be the protonated form. So there were formulas was discussed to find out the ionization fraction, and ionization fraction depends upon the pK's values of the acid and H plus concentration. And for monoprotic acid, there will be 2 ionization fraction. For diprotic acid, there will be 3. And for triprotic acid, there will be 4 ionization fraction depending upon the number of H plus or number of species of that acid that will present at different pH. The second lecture was about visual Mintek, in which it was introduction about visual Mintek was given. It is a free software which can be installed, and it is used to find out the pH or do the thermodynamic analysis of the of our system. In the third lecture, there were some examples discussed by using Visual Mintek, how the interface of Visual Mintek appears to the user, how we can find the pH, and how we can feed the total concentration of different components. It was discussed in the third lecture of the week 4. And in lecture number 4, there were mixing problems in which there two different solution having different acids were mixed, and final pH was determined using Visual Mintek. And the last lecture was about inverse dose problem, in which the pH was given, and the question was like, find out how much acid should be added to lower the pH or increase the pH. So this was the inverse dose problem. So in this lecture, we will need the use of Visual Mintek. So I have already added the solution by solving the question in Visual Mintek, but I will try to give you solve the questions live on Visual Mintek, so that you get a essence of how to solve the questions. So we will see the first question. So the first question is, a monoprotic acid dissociates in water as below, and the pK for the dissociation of HA acid is given. The concentration of deprotonated form and total concentration of the acid at equilibrium are given, and we have to find out the pH of the solution. So this question is based on Henderson, Hazelback equation, which gives the relation between pH, pK and concentration of the deprotonated form to the protonated form. Here in this question, we have been given the deprotonated form as 10 raised to power minus 4.8, and the total concentration of the acid is given as 10 raised to power minus 3.5. So as we know, the total concentration is equal to the sum of the deprotonated form and the protonated form. So we can find out the deprotonated form as by subtracting the concentration of the deprotonated form from the protonated form. By subtracting the concentration of A minus from the total acid concentration. So now we can write in the Hazelback equation, pH equals to 3.29 plus log AC minus is 10 raised to power minus 4 upon 10 raised to power minus 3.5 minus 10 raised to power minus 4.8, which is giving the final answer is 2.012. So D is the correct answer. So let's move to the next question. So the second question is, acetic acid dissociates in water as below. The pH of the resulting solution is 5. The concentration of acetate ion at equilibrium is given. Calculate the total concentration of acetate in the solution at equilibrium. So we can see here that the total concentration of the acid has to be calculated. Concentration of AC minus is given, pH is given, and pK given. So as we know from Henderson, Hazelback equation, it gives the relation between pH, pK and the protonated and deprotonated form of the acid. Concentration of the protonated and deprotonated form. So here from the question we have given pH is 5, pK is 4.76. We have been given the concentration of the A minus, that is 10 raised to power minus 2.3, and total and the protonated form of AHA we can find from this relations, which give the concentration of HA as 10 raised to power minus 2.404. But here we have to find out the total concentration of the acetate. We have to find out AC total, which will be the sum of protonated form and deprotonated form. So we have calculated HAC as 10 raised per 2.404. A minus is given as 10 raised per minus 2.3. So by adding it, we are getting AC total as 10 raised per minus 2.05. So the closest option is option A. So Sudarshan Viraji, can you hear me? Is the slide visible and I am audible? So I think Sudarshan Viraji is not available. So we'll move to the next question, which is question number 3. Okay. So question number 3 is compute the pH of 5 into 10 raised per minus 8 molar HCl solution. Ignore the effect of ionic strength and assume that AI equals to Ci, which means that the concentration of the deprotonated form is equal to the total concentration of the acid. So we have been given HCl, and as we know HCl pK value is negative. So as soon as HCl goes in water, it will dissociate as H plus and Cl minus, and Cl minus concentration and H plus concentration will be equal to the initial concentration of the acid added. So I request Sudarshan Viraji to try to solve this question, and I will give you around 5 minutes to solve the question and write your answer, what value you are getting in the chat box. Okay, no problem. I will solve this question in stepwise because there are various steps, and to solve the question related to pH, the steps are generally common. We just have to follow the steps, and then we can come to the final solution. So we have been given the HCl solution. First, for solving any question related to pH, we will write the what are the species and components in our system. So first we will write the species. So we have HCl solution, nothing else is there. Sorry. So species will be H plus, OH minus and Cl minus. Of course, H2 is also the species, and components will be H plus and Cl minus. To solve the question related to pH, species and components should be very clear, because from this combination of species and components we can find out how many unknowns are there and how many equations have been given, whether the question can be solved or not. So, and also for HCl we know pKa of HCl is less than 0, which is given as a form of hint in the last statement of the question, that assume AI equals to Ci. So since pK is less than 0, it means it will dissociate completely. That means the concentration of Cl minus will be equals to the total concentration of acid, that is 5 into 10 raised per minus 8 molars. Now we will form the tableau in which we will see. So here we will write the components, which is H plus and Cl minus. In the vertical column we will write the species. We have H plus, we have Cl minus and we have OH minus as the species. Now, all these are coming from HCl naught. So from H plus we will have 1 H plus and 0 Cl minus. From Cl minus there is 0 H plus and 1 Cl minus. OH minus, for it will be minus 1 and Cl minus will be 0. And from HCl 1 H plus is given and 1 Cl minus is given. Next move to the formation equations. So we will write the component mass balance. Components are H plus and Cl minus. So total H plus will be H plus 1 H plus minus OH minus, and that is equal to the HCl naught concentration, that is initial total concentration of the acid. And similarly we can write the component mass balance for chloride, which is equals to Cl minus, and Cl minus is equal to total HCl concentration. So we will give this as equation 1 and this is equation 2. So we'll try to solve equation 1. We have H plus minus OH minus equals to HCl naught. So let's move to next slide. Just let me add a blank slide here. So we have to solve this equation. So we have H plus let's write first the formula formation equations for H2O. H2O dissociates into H plus and OH minus, and Kw is 10 raised power minus 40. So we can write equilibrium constant in terms of species of H plus and OH minus divided by, sorry, activity of the H plus and OH minus divided by activity of H2O, and we know that activity of water is 1. So Kw is equals to activity of H plus and activity of OH minus, and for dilute system we can take activity as equal to concentration. So Kw will be concentration of H plus and concentration of OH minus. So here we can write that concentration of OH minus is equal to Kw upon concentration of H plus, that is 10 raised to power minus 40 upon H plus concentration. So we were having equation 1 as H plus minus OH minus is equals to HCl naught. So let's put everything here. We have OH minus as 10 raised to power minus 14 upon H plus, and we have HCl naught as 5 into 10 power minus 8. So now we just have to solve this equation. We will have a quadratic equation, that is H plus square minus 5 into 10 raised per minus 8 H plus minus 10 raised per minus 14 equal to 0. So it is a quadratic equation where H plus is the unknown. We can solve this equation and we will get the value of H plus. So after solving, we are getting H plus as 1.281 into 10 raised per minus 7, and as we know pH equals to minus log activity, or since the system is diluted, we will take it as concentration of H plus, which will be minus log 1.281 into 10 to the power minus 7, and we will get the pH as 6.892. So this is the final answer. So is the question, Sudarshan Viraj, can you now understand how to solve this question? So I think there is some network issue. So I'll move to the next question. Question number 4. Cyanide ion is vital in metal plating industries because it can keep metals dissolved under conditions where they would otherwise form solids and settle out of solution. It is essential to maintain pH greater than 10.5 in these solutions to minimize the release of toxic hydrogen cyanide gas. If a solution is prepared by dissolving this much of NaCN in water, select whether the below statement is true or false. The pH of the solution will be in the range to minimize the release of toxic gas. So cyanide is used in metal plating industries, and the pH should be greater than 10.5 to reduce the release of hydrogen cyanide gas. So here we have been given a condition is that we are adding about 10 raised per minus 2 molar of NaCN in water, and we have to tell that whether the pH will be suitable for release of toxic gas or not. So if the pH will be greater than 10.5, then there will be very less or no release of toxic hydrogen cyanide gas, and if it will be less than 10.5, then there will be release of hydrogen cyanide gas. So this is also a similar question like previous one. So please try to solve this question and tell me what pH you are getting after solving the question. So I'll give you around 5 minutes to solve this question also. So take your time and write your answer in the chat box. So let's see how to solve this question. So we have been given that we are adding 10 raised by minus 2 molars of NaCN in water and we have to find out the pH. So there is no pK value mentioned. So we will solve this question using Visual Mintek. I hope that you all have installed the Visual Mintek and we will see how to find the pH in Mintek software. So first let's see what is given in the question. It is given that we have added sodium cyanide is 10 raised per minus 2 molars. This much of sodium cyanide we have added in the system. So we can see that W I can just make. So we have the components as H plus, Cn minus and Na plus. Species will be H plus, Cn minus, OH minus and Na plus. But here nothing is, we are adding NaCN, so it will not give any H plus, so we will not do the component balance on H plus and OH minus ions. So H plus will give us 1 H plus, 0 Cn minus, 0 N plus. It will be 0, 1, 0, minus 1, 0, 0, 0, 0, 1, and we have added NaCN. It will give 0 H plus, it will give 1 Cn minus and 1 Na plus. So we have to do the component balance on Cn minus and Na plus. So total Cn minus concentration would be, we can write it as total Cn as, it will be equals to NaCN naught, what we have added initially, and that is equals to 10 raised per minus 2 molars. And for Na plus, total N sodium ion in the system will be equal to total Na plus equals to NaCN initially added, that is equals to 10 raised per minus 2 molars. So we will feed these two values in the Visual Mintek and we will solve the pH. Let's see. So I will stop sharing here and I will open the Visual Mintek software. We can see the the first page which opens it as, we have pH, we have ionic strength, we can add the component name here, we can add input the total concentration of each component. Then we have different units for concentration. We have temperature, we usually do at room temperature, so temperature here will be 25 degrees centigrade. Then we have to run the Mintek and see the result. So let's start. So our first component is Na plus. So we will go to sodium. We will search for Na plus here. So I can see Na plus here. So its concentration is 10 raised per minus 2. So let's first select the unit which is already molar. So it is 0.02. Sorry, 0.01. We will add to list. Similarly, now we will add cyanide, that is Cn. So we will search for Cn. Here is the Cn. It is also 0.01. We will add to list and we can see our list from here, view or edit list. So we can see that Na plus is 0.01, Cn minus is 0.01. We have not added H plus, so it is showing as 0. So we'll go to back to main menu. We will run the Mintek and we can see that we are getting the pH as 10.547. We have also got the ionic strength as 10 raised per minus 2, and this is the species, different species present at equilibrium, the concentration of each species, and also the activity is given. So here we have taken the H plus and we can see that the concentration of H plus is very less. So we have ignored that. So it is correct assumption. And we can also see that NOH is also less than OH minus and Cn minus. So it is also a correct assumption. And we can also see equilibrated mass balance distribution. Here it shows the total dissolved, percentage dissolved, and these are, we will see in the subsequent week when there will be discussion about solids precipitation and all. So we'll go to back to main menu. We can see here various species distribution. Na plus and Cn minus follows the component, and we can see that around 99.96% of sodium is staying as Na plus, and around 96% of cyanide ion is staying as Cn minus, and only around 4% is staying as HCl minus. So by solving in visual Mintek, we get to know about what are the species and what are its concentration, what is the activity of each species, and so on. So here we get the pH as 10.547, and the pH we get was 10.547, and here it is said that if the pH is greater than 10.5, then there is no release of toxic hydrogen cyanide gas. Final pH we got was around 10.547, which is greater than 10.5. So there will be no release. So the release of toxic hydrogen cyanide gas will be very less. So the statement is the pH of the solution will be in the range to minimize the release of toxic gas. So this statement is true. So the correct option is A. Okay. Let's move to the next question. So I have also added the screenshot of the visual minting in the slides. This will, in the slide which I will share, this will be there in the, these will be there in the slides, so you can see and also check whether you are doing the correct calculation or not. So let's move to the next question. So in question number 5, the question is, a solution is formed by mixing an equal amount of sulfuric acid and sodium sulfate in water. Initial concentration of H2SO4 and Na2SO4 are given. Assume both the compounds dissociate completely and can be neglected at equilibrium. Find the pH of the resulting solution. So we have been given that we are adding two things, that is sulfuric acid and sodium sulfate in water, and we have given the concentration of each of these, and it is also given that both of these compounds dissociate completely, so we can neglect the H2SO4 and Na2SO4 as a total in the system, and we have to find the pH of the resulting solution. So it is also similar to the questions which we are solving. So first I want you to write the what are the species and what are the components present in the system. Because if we are clear about the species and components, then we can solve the question very easily. Because in the components we apply the component mass balance. So if we know what are the components and what are the species, then we are in the right direction to solve the question. So Sudarshan Viraji, I will request you to first write the species in the chat box. Sorry. So I will give you around 2 minutes to write the species. First, write the species in this system. Just write the name of the species in the chat box, or also you can unmute yourself and just say what are the species and components present in our system. So let's see what are the species and components present. So species will be, obviously we are doing the calculation in water. The phase is aqueous phase, so species will be H plus and OH minus. These two will be definitely present at equilibrium. And also we will have sulfate and we will have sodium, because we are adding H2SO4 and Na2SO4 in the water. So sulfate and sodium will also be present at equilibrium. And components, and as we know, components are the building block of the building block of our system. Like if we know sulfate, then by adding hydrogen in this, we will get the H2SO4, we will get HSO4 minus, and if we have Na plus as the component, then we can get Na2SO4 from this. So
H plus H2H.
H plus,
HSO4 minus.
um, generally the practice is to take the most deprotonated form as the component. So we will take sulfate SO4 2 minus as the component. And there is one more, we are
Oh,
adding sodium sulfate. So Na plus will be the one of the components. So we have three components, four species. So we can also prepare the tableau for this. Let's see that. First we will write the species here. Species are H plus, OH minus, SO, SO4 2 minus and Na plus. These four are the species, and we have three components, that is H plus, SO4 2 minus and Na plus, and we are adding two compounds here, that is H2SO4 and we are adding Na2SO4. So from the formulation equation we will know that H plus will give us 1 H plus, why the cursor is not working, 0 SO4 2 minus and 0 sodium ion. For hydroxide ions we will have minus 1 plus, because as we know H2O will give us H plus and OH minus ions. Kw will be, sorry, from here we can write that OH minus ions is equal to H2O minus H plus. Since 1 H plus is subtracting, so we will have minus 1. There will be 0 sulfate because it is not involved in the reaction, 0 Na plus, and here again 0, 1, 0, 0, 0 and 1 sodium ion. And H2SO4 will give 2H plus. Finally, it will give 2H plus and 1 SO4 2 minus. And it will give 1 sulfate ion and 0 sodium ion. And Na2SO4 will dissociate and it will give 2 Na plus and 1 sulfate ion. So H plus will be 0, sulfate ion will be 1 and Na plus is 2. So from this table we can say that total H plus will be equal to concentration of H plus minus OH minus, and that this will be equal to 2 times total H2SO4 added initially, that is equals to 2 into, we are adding 10 raised to power minus 3 moles of H2SO4. So this is the total H plus added. And next we will do the component balance, mass balance on sulfate. Let's see, SO4 2 minus, it will be equal to 1 times of initial H2SO4 added plus 1 time of Na2SO4 added, which is equals to 10 power minus 3 plus 10 to power minus 4. After adding this, we will get 1.1 into 10 to the power minus 3 molar of sulfate. And next we will do the component mass balance on sodium, and it will be equal to total Na plus. So here we can see that for sodium it is equal to Na plus concentration, which is equal to 2 times of Na2SO4 added, equal to 2 times of Na2SO4 initially added, which is equal to 2 into 10 raised to power minus 4 molars. So let me write all the total concentration of H plus here, and it is equal to 2 into 10 to the power minus 3 m, and we have sulfate, it is equal to 1.1 into 10 raised to power minus 3 molars. So now we have to add these components and write their values in the and we have to add these components in the visual Mentec along with their concentration, and then we just have to run it and we will get the pH. Let's see. We have to add, so since we have solved the previous question, we can do the reset from here. It will reset all the components added. So we have to add the pH from mass balance. Ionic strength is to be calculated. So let's add the component. So our first component is H plus, and we have, let's first add H plus. So we have H plus, we will see the unit, it is molar only. So H plus is 2 into 10 raised per minus 4. So it is 0.0002. We will add to list. We will add the next component, that is sulfate, and it is equal to 1.1 into 10 raised per minus 3. So, and next component is sodium, and sodium is equal to 2 into 10 per minus 3. We will add to list. We will see all the list. We have H plus as 0.0002, that is 2 into H plus is 2 into 10 per minus 3, sorry, so we will edit here. And sodium is 2 into 10 per minus 4, so one more 0 here. So I'll go to back to menu and we will run Mintec. And we are getting the pH equals to 2.756. So let's go back to the slides. 2.756. So option D is the correct answer, that pH will be 2.75. Let's move to the next question. So the question is, significant inhabitants of a city suddenly suffer from a waterborne disease. As being an environmental engineer, you are advised to check various parameters of potable water supplied across the city. Parameters include both chemical and biological. After assessing the influent and effluent of the water treatment plant, you found out a class of bacteria present in water causing the outbreak in the city. Luckily, after laboratory testing, it was noticed that bacteria only survive in alkaline water, typically for potable water. To control pH, 6 into 10 raised per minus 4 molar HPR is added, that is propionic acid is added, which reduced the pH of water to 4.081, which destroyed a significant population of bacteria. To neutralize water for domestic use, this much of NOH is added. pH increased slightly, and for decreasing more H plus ion concentration, again 2 into 10 raised per minus 4 molar NaPr salt is added to water. What will be the pH of the solution? So in this question, we can see that we are adding number of compounds in, we can see in a series term. Like first we are adding the HPr, then its pH has reduced to 4.08, which destroyed the pathogens, that the bacteria. And then to neutralize the pH, again NOH is added, and since NOH resulted in very high increase in pH, so again to reduce the pH, NaPr is added. So we have to find out the what will be the final pH of water. So we can see that this question is very complex and very complex to solve manually. So we can solve this question very easily by using visual Mintek. We just have to do the component mass balance on the various components, and we just have to put the values in the visual Mintek, and it will do the calculation for us. So let's see the components and do the mass balance for them. So first component will be, let's just write the components. So we will have H plus, we will have C2H5COO minus, we will have Na plus, yeah, or also we can write this in the short form as Pr minus. So we have three components. We will do mass balance on these three components and put the value in the Mintek software. So let's see the total H plus added. Let's first write what is the concentration we are adding. We are adding C2H5COOH as 6 into 10 raised per minus 4 moles per liter. And then we are adding NaOH as 3 into 10 raised per minus 4 m. And then again we are adding NaPr as 2 into 10 raised per minus 4 m, or we can also write as HPr. So total H plus will be given from C to HPr and not from NOH and not from NaPr. So total H plus will be, sorry, also Na, we have NOH, and from the species table we know that 1 mole of OH minus takes 1 mole of, reduces 1 mole of H plus. So total H plus here will be, we have added HPr minus NaOH. So HPr we have 6 into 10 raised per minus 4, and NOH is 10, 3 into 10 minus. So after solving, we will get 3 into 10 raised per minus 4 m as total H plus. Next we will do the component balance on PR total. We will get PR from this C2H5COOH and NaPr. So it will be C2H5COOH plus NaPr. So we are adding 6 into 10 raised per minus 4 molars of this and 2 into 10 raised per minus 4 molar of this. So overall we have 8 into 10 raised per minus 4 molar of Pr minus in our system. And last we will do on the third component, which is sodium. So each mole of NaOH will give 1 mole of Na plus, and each mole of NaPr will also give 1 mole of Na plus. So it will be NaOH plus NaPr, which will be 3 into 10 raised per minus 4 plus 2 into 10 raised per minus 4, which will give us as 5 into 10 raised per minus 4 m. So finally we will put these components along with their concentration in visual intake, and we will run the software and we will get the final pH. So first we will reset, and then we will add the concentration of H plus, which was 2. So H plus was 3 into 10 raised per minus 4, that was 0.0003 molars. We will add. Next we have Na plus, and Na plus is 5 into 10 raised per minus 4, so I'll just add 5 here. Again we will add to list, and finally we have propionic acid. So for that, here is show organic components, so we will tick this, and then we will get the propionic acid will be from P, so we will go down. So here it is propionate, and propionate is 8 into 10 raised per minus 4, so here 8. We will add to list. We can check the list here. We have added H plus, Na plus and propionate. We'll go to back to main menu. We will run the intake, and we are getting the final pH as 5.103. So let's go back. pH is equals to 5.103. So which is option A. Option A is the correct answer. So let's move to the next question. So question number 7 is, hydrofluoric acid is a weak acid whose pK value is given as 3.17, that is used extensively in industry because fluorine ion attaches firmly to ferric and aluminium ions. As a result, it is an excellent reagent for removing surface scales from objects made of iron and aluminium before they are painted or other surface finishing operations are carried out. Compute the pH in a solution prepared by adding 10 raised per minus 3 molars of HF to pure water. So again we have been given that hydrofluoric acid is used in removing surface scales from object made from iron and aluminium, and we are adding around 10 raised per minus 3 molars of HF to pure water. There is nothing else in the system, and we have to find the pH. So this question is also similar to the previous questions which we have solved. Let's see how we can solve this question. So let's write what are the species here. Species will be H plus, OH minus, and we are adding HF to pure water, so F minus. And we will have components. The components are H plus and F minus. We can prepare the table for this. So we will write the species H plus, OH minus, F minus, and write the components here H plus and F minus. And then we are adding HF in pure water, so H plus will have 1 H plus, 0 F minus, minus 1, 0, 0, 1, and HF we are adding, which will give 1 H plus and 1 F minus. So we can write the formation equations. H2O is giving H plus and OH minus. HF is given H plus and F minus. So here the kW will be 10 raised power minus 14. Here pK is given as 10 power 3.17. So Ka will be 10 raised power minus 3.17. And now we will do the component mass balance, that is H plus H total will be equal to H plus minus OH minus, H plus minus OH minus, and it will be equal to HF initially added in the system, and it will be, since HF minus added is equal to 10 raised power minus 3 m. And next we will do the component mass balance on F total will be equal to, F total is equal to HF added in the system, that is equal to 10 raised power minus 3 molars. So we can solve this question in the visual Mintech also, or we can solve it manually. So till now we have seen how to solve the question in visual Mintech. So we will see this question how we can solve manually. So let's do. So let's number this as equation 1 and this as equation 2. So from equation 1 we have total H concentration in the system is equals to H plus. So I have done a mistake here because from HF we will get 1 H plus. So here it will be H plus minus OH minus plus HF. So let me just rub this. So let's do these in a separate page. I'm sorry. So H total will be H plus minus OH minus plus HF, because one HF will dissociate to give H plus and F minus. So this is equal to total HF naught, which is equal to 10 raised power minus 3 m. Next for HF F total we will see it will be equal to F minus plus HF. which will be again equal to 10 raised power minus 3 m. So from equation 1, we can solve this question. So we have H plus minus OH minus plus HF equals to 10 raised power minus 3 m. So let's move, and as we know from the uh, acid ionization constants, for monoprotic acid alpha naught is equal to H plus upon Ka plus H plus into total concentration of the acid, which is 10 raised per minus, sorry, this is the value for alpha naught, and here we can write H plus minus Kw upon H plus HF. It can be written as alpha naught into F total equal to 10 raised per minus 3. So H plus minus Kw upon H plus, and alpha naught is H plus upon Ka plus H plus into F total is 10 raised per minus 3 equals to 10 raised per minus 3. So we can see that if we are solving this equation, we will get a cubic equation. So anyhow, we can solve a cubic equation, but we can also simplify this question. So since it is given that the pKa value is what it was, 3 pKa value was 3.17. So we are adding an acid, so we can expect the pH to be less than 7. So if pH will be less than 7, then we can neglect the hydroxide ion concentration. So we can neglect it to 0. So it will be also neglected it to 0. So now we can see that our equation is simplified. We have H plus, and we have H plus upon K plus H plus into 10 raised per minus 3 equals to 10 raised per minus 3. So after solving this equation, let's solve this. We will multiply here. So H plus square plus Ka into H plus H plus into 10 raised per minus 3 equals to Ka into 10 raised per minus 3 plus H plus into 10 raised per minus 3. So all these two will cancel, and we will have the final equation as H plus square plus Ka H plus minus Ka 10 raised per minus 3 equals to 0. So we can see that it is a quadratic equation, and after solving this we will get the final value of H plus. So after solving this, we will get H plus as 5.5 into 10 raised power minus 4, and pH will be equals to minus log concentration of H plus, which is equals to 3.259. So here we can see that we are getting pH around 3.2, and the assumption which we assume that the concentration of OH minus is very less is true, because if concentration of H plus is 10 raised per minus 4, the concentration of OH minus will be 10 raised per minus 14 plus 4. It will be around 10 raised per minus 10, which is very small in very small quantity. So we can neglect OH minus here. So I hope this is clear. Let's move to the next question. So next question is, a solution is made by adding 10 raised per minus 3 molars of HOCl and 10 raised per minus 3 molars of NaPr, that is sodium propionate, to water. When NaPr is dissolved, sodium ions are released and undergo no further reaction. It means when NaPr is added, it is dissociating completely as Na plus and Pr minus, and it is not going any further reaction. Then NOH is added until the solution pH is 7, and after NaPr we are adding NOH so that the final pH of the solution is 7. So we have to find out how much NOH must be added. We have been giving the pKa value for HACl and pKa value for HBr. So till now what we were doing at that, we were given some system. It was given that we are adding this much concentration of some particular acid or base or salt, and we were finding the final pH of the system. Now in question number 8 we can see that we have been given a system, we are adding some salt or some acid, and we are given that the final pH is 7. We have been given the pH of the system, and we have to find out how much base, that is NOH, we must add in the system. So we have to do back calculation. We have to find out the quantity of NOH added to get the final pH is 7. So let's see how we can solve this question. We are adding HOCl, concentration adding is 10 raised to power minus 3m, and NaPr which is being added is 10 raised to power minus 3m. So again we are adding NOH in the system. So let's first write down what are the species and what are the components present in the system. So species are H plus, OH minus, HOCl and OCl minus, and next we have Na plus, HBr and Pr minus. And let's write components. So component will be H plus, OCl minus, Pr minus and Na plus. So we have 7 species and 4 components. Let's write the corresponding reaction for the system. So first we will write for water. It will dissociate as H plus and OH minus, and the Kw will be 10 raised to power minus 40. Next we will write for HBr. So it will give H plus and propionate ion, and here the pK is given as 10 raised to power minus 4.87. Let's number it as or let's not do anything, keep it as Ka. And we have HOCl which will be H plus and OCl minus, and let's give this name as Ka dash as 10 raised to power minus 7.53. Now let's write down the equilibrium relationship for these 3 equations. Equation 1, 2 and 3. So we will from equation 1 we can write the Kw as concentration of H plus into concentration of OH minus equals to 10 raised to power minus 14, because we know that activity of H2 is taken as 1, so it is removed from the denominator. And from equation 2 we can write Ka as H plus into Pr minus upon HPr equal to 10 raised to power minus 4.87. And from the third equation or third reaction we can write K dash as H plus into OCl minus upon HOCl equals to 10 raised to power minus 7.53. So we have 3 reactions and corresponding 3 equilibrium relationship. So now we can see, let's move to the next part. We have written the species, we have written the components, we have written the equilibrium relations for the reactions, and next we will write the mass balance for the components in our system. So first we will write the mass balance for PR total. It will be HPR plus PR minus, and we are adding 10 raised to minus 3 m. And now we will write the, let's write here, component mass balance. OCl total will be equals to HOCl plus OCl minus, and it will be equal to 10 raised to minus 3 m. And next for sodium, it will be equal to NOH plus NaPr. Now let's take this as C, because we know the amount of NaPr added, but we have to find the amount of NOH, so let's take it as C. Now we will write charge balance for the system. So in charge balance, total positive charge should be equal to the total negative charge in the system. So the cations here we have H plus, we have Na plus, and anions we have OH minus, we have Pr minus, and we have OCl minus. So we have been given H plus. So let's solve this. We have H plus Na plus. We can write OH minus in the terms of Kw upon H plus. We can write Pr minus as alpha naught Pr total, and we can write OCl minus as alpha naught dash then OCl total. So here we can write Kw upon H plus. Alpha naught is equal to Ka upon H plus Ka, and Pr total is 10 raised to power minus 3 plus alpha naught dash. Let me see which I have taken dash as, so I am going correct. I have taken K dash for HOCl. So again it will be Ka dash upon H plus Ka dash, and OCl total is 10 raised to power minus 3. And we have been given that the final pH is 7. So for pH 7, H plus will be 10 power minus 7 plus Na plus. So let's do 10 raised to power minus 7 plus Na plus. It will be 10 raised to power minus 14 plus 7. Any of these two will cancel out. And we will have to solve this where Ka is given as 10 raised to power minus 4.87 upon pH is 7. So concentration of H plus will be 10 raised to power minus 7 again. And similarly for Ka dash, we have been given 10 raised to minus 7.53 into 10 raised to minus 3. So by solving this, we will get total Na plus concentration as 1.2205 into 10 raised to minus 3 m. Let's move to the next slide. Now we have to find out how much NOH we have been adding. So as we know that Na total is equal to NaOH plus NaPr, and we are getting the Na total as 1.2205 into 10 raised to minus 3. We have to find out how much NOH we are adding, and we are adding 10 raised to minus 3 molar NaPr. So on solving this, we will get NOAH added as 1.2205 into 10 raised to minus 3 minus 10 raised to minus 3, which is coming out to be 0.2205 into 10 raised to minus 3 m, or we can write it in the form of 2.205 into 10 to the minus 4 m. So this much of NOH have to be added in the system to get the final pH as 7. So let's move to the next question. So it is a mixing problem which says what will be the pH of 100 ml of a 10 raised to minus 3 m solution of sodium hypochlorite, to which 20 ml of 2 into 10 raised to minus 3 m HCl is added. So we are mixing two solutions. One is NaOH, sodium hypochlorite, and we are adding HCl solution. So again, in mixing problem, pH is not conserved, but yes, the concentration of the various components are conserved. So we will first see the concentration of the various components in the mixture, and then we will try to find out the final pH. So here it is given that, let's name solution 1. So in solution 1, we have been given the volume as 100 ml, and in that solution we have NaOCl concentration as 10 raised to minus 3 m. We have solution 2, its volume is 25 ml, and HCl concentration is 2 into 10 to the minus 3 m. So we have mixed solution 1 and solution 2, so we will have mixture, or we can write it as mixed solution. Its final volume of mixed solution will be V1 plus V2, that is 100 plus 25, 125 ml. So in the after mixing solution 1 and 2, we will find out the concentration of the various components in the system. So we will have components NH plus, we will have OCl minus as the component, we have Na plus as the component, and we will have Cl minus as the component. Let's do the mass balance for each of these components. Let's start with H plus. So we can see that in system 1, NaOCl is not giving any H plus, so it will be 0, into volume of the system will be 100, and in solution 2 we have 1 mole of HCl give well 1 mole of H plus and 1 mole of Cl minus. So it will be 2 into 10 per minus 3 moles of H plus into volume 25 upon volume of the mixed solution, that is 125. So after solving this, we'll get the H plus concentration as 0.4 into 10 raised per minus 3 m. Next, we will do the component mass balance for OCl minus. In the solution 1, we have 10 raised per minus 3 OCl minus into volume will be 100. But in solution 2, there is 0 HOCl minus into volume will be 25 upon total volume. We are getting OCl minus as 0.8 into 10 raised per minus 3 m. Next, for sodium, and finally we will write for Cl minus. In the solution 1, there is 0 Cl minus. So we got 4 components. We will put the total concentration of these 4 components in visual Mintek and we will get the final pH. So let's see how we can get the final. Go to visual Mintek, I'll reset it. Then I will add my components one by one. So my first component was H plus. So I have H plus as 0.4 into 10 raised per minus 4, that is this. I will add it to the list. Then I have OCl minus. So OCl minus I have here. It is equal to 0.8 into 10 raised per minus 3. So here I will add it to the list. And then I have Na plus. And Na plus is 0.8 into 10 raised per minus 3. So I will remove 1 0. I will add it to the list. And finally I have chloride ion. And it is 0.4 into 10 power minus 3. So I will check my list. So I have done a mistake. Na plus will be also 0.8 into 10 raised per minus 3. I will go to main menu. I will run the Mintek and I got the final pH as 7.515. So let's go back to our slide. pH was 7.515. So let's move to the next question. So the question is, you have a flask in your laboratory on which the label is smudged. From what you can read, it is a solution of monoprotic acid. It is called as HX at a concentration of this in a 0.05 m NaCl solution. You measure the pH of the solution and get a reading of 3.09. Determine the pK of the acid. Again, we have been given the pH of the solution and we have to find out what is the pK of the acid. So similar to question number, I think 8, where we calculated the concentration of NaOH added. So in this question, we have to find the pKa value, and the steps will be very much similar to the steps which we followed in question number 8. So let's see. how we can solve this question. So we have been given Hx, sorry, total Hx concentration is 2 into 10 raised to power minus 3 m. And we have NaCl as 0.005 m, and we have been given the pH as 3.09, and we have to find out what is the pK of the acid. And Hx will give us H plus and X minus, and in the question it is asked we have to find out what is pK, what is Ka. And we know pKa is minus log of Ka. So let's see. Each mole of NaCl will give equal 1 mole of NaCl give will 1 mole of Na plus and 1 mole of Cl minus. So we can write that Na plus concentration equals to Cl minus equals to initially present in the system 0.05 m, and we will do the component mass balance for Hx. So we can write that total X will be Hx plus X minus, and it is a monoprotic acid, so if we will H0 and H1 we will use these two. Let's do the charge balance for the system. So we have H plus, we have Na plus as the cations, and the anions is OH minus, Cl minus and X minus. So Hx is the monoprotic acid, so X minus will be given as alpha 1 times of total X concentration. So we have been given the pH is 3.09, so H plus concentration will be 10 raised to 3.09. We have sodium concentration as 0.05. We can write Kw is H plus into OH minus, so OH minus will be Kw upon H plus. So 10 raised to power minus 14 upon H plus is already given, 10 raised to power minus 0.39. Cl minus is given as 0.05, and X minus we will write it as X1 X total. So this and this will cancel out. Let's solve it further. So we have 10 raised to power minus 3.09 minus 10 raised to power minus 10.091. By doing this, minus 14 plus 3.091, and we can write alpha 1 as Ka upon Ka plus H plus into X total. So we have to find out Ka. pH is given, so we can write it as 10 raised to minus 3.09, and also X total is given as 2 into 10 raised to minus 3. So we just have to solve this equation. We have to solve this equation and we have to find the value of Ka. So after solving, we will get Ka as 10 raised to power minus 3.2545. So let's see the options given. So option B will be the correct option, that is 10 raised to power 3.25. So as I have told you, pK is nothing but minus log of Ka. So minus log of 10 raised to power minus 3.3245 will give us the value as 3.2545. So this is the correct answer. That is B is the correct answer. If you have any doubt, you can ask, unmute yourself and ask, or otherwise we will end the meeting here. So thank you so much for joining. Have a nice day.